Are we recording?
I just hit record.
I already said things. Hi, my name is Linnea.
I'm Bezia.
And I'm Linnea. And this is episode number 16 of the Lemma Journal Club.
Shh, God damn it. We have another algae paper for you today, a map of the Rubisco biochemical landscape.
This is not algae. This is Rubisco. Rubisco is found in plants as well as algae.
Okay, I have a complaint.
And bacteria.
I have a complaint from so I've been listening to previous episodes, and then I listened to some of the algae episodes, which you say are not algae episodes, and those are unfun episodes, because the best case scenario is that I'm thinking about some like coming global warming apocalypse while reading these papers. If we're going to keep doing papers like this, we need to come up with some sort of game to liven these ones up. This is, as you said, it's a paper about Rubisco. What is Rubisco, Linnea?
Rubisco is the most abundant enzyme on the planet, Bez.
How many times do you think you've said that sentence?
I think I heard it for the first time from Peter Foster, like when we were grad students at the Active Matter Physics Conference.
Oh, wow. Okay.
And I was like, what? What is Rubisco? I don't know what that is. And then I started studying it, and now I say the sentence a lot.
So we're going to be really quiet this episode because our baby's asleep and she's going to wake up at any moment, and that's going to be the end of the episode. Lenny is already generally very quiet, and we have to boost her levels post. So if Lenny sounds super like vocal fry, what's happened is that a whisper has been pumped up to sound like it sounds like a normal level of speech. What does Rubisco do as the most abundant protein on the earth?
Rubisco converts CO2 into biomass, into sugar. Yeah, as the part of the dark reactions in photosynthesis.
So this paper,
Calvin-Benson-Basham cycle.
This paper is by Noam, Prywes, and then 20 other people, whatever. Correct me if I'm wrong. The main thing about this paper is that they got plant Rubisco into E. coli.
It's not plant Rubisco.
It's not plant Rubisco.
It's bacterial Rubisco.
It's bacterial Rubisco.
Which I thought was a weird, I thought that was a weird choice.
Okay, but they got bacterial Rubisco into E. coli.
Yeah. There's bacteria that do photosynthesis, right?
Okay.
Yeah, the most famous are cyanobacteria. This, I think, is not a cyanobacteria. It's just some other bacteria that does photosynthesis.
Okay. And so by getting successfully bacterial Rubisco into E. coli, because E. coli are the workhorse of modern science, they're able to do this mega assay of thousands and thousands of different E. coli mutations.
Yeah, and I think their big hack here is that they've modified the E. coli metabolism so that it needs Rubisco in order to survive.
Okay, I see. Then that's what this figure 1A is.
Well, I was unclear about whether this was a new technique.
I think
because they had some citations saying that people had tried similar things.
Okay, so maybe it's not a new technique. The main thing that's presenting is this resource of thousands of single amino acid mutations on the bacterial Rubisco to see how that changes the Rubisco's function.
Yeah.
I don't think that this is a great way to go about seeing how you can get more efficient Rubisco, right? They're trying to mutate to make a more efficient Rubisco. I don't think they do either. This is the first step.
I think this is a proof of principle.
Yeah. They go into the structural stuff where they say, hey, this is where the amino acid is on the protein, because there exists on PDB, on the protein database, a real measured shape of the protein in its non-mutated form. It's not so good at this, but I really would have liked to know if when you put each mutation through AlphaFold, did it ever predict a significantly different structure? They don't really see any positional relation.
There's like the obvious thing of if you are at the active loop, then you can't make a mutation. And otherwise it was like much more kind of all over the place. And
so then experimentally, what exactly were they measuring for the Michaelis-Menten kinetics? So sometimes they purified the Rubisco in cases where they really wanted to know what was going on and did some assays to really learn the Michaelis-Menten kinetics.
Yeah.
At the population level, where they did the broad screening of all the different E. coli, what were they experimentally measuring?
Yeah, so they were changing the CO2 concentrations.
Okay.
And they were measuring the Rubisco flux at each CO2 concentration.
How much Rubisco gets made?
Kind of. They explain this in figure 1, I thought, which is they get from a growth curve, essentially, like the slope of the growth curve. Okay. They do some control experiments, which they say shows that the growth of Rubisco is linearly proportional to the Rubisco flux.
But they calculate three things, essentially. They calculate Vmax. Vmax is the effective maximum rates. It's the Vmax before the Michaelis-Menten equation.
Yeah.
Then they calculate K sub C, the half saturation constants. That's the K sub C on the bottom of the equation, right? How are they getting Vmax and K sub C out of this growth curve?
They're changing the CO2 concentration and they're measuring the Rubisco flux. They in C through E of this figure of 3C, they have these y-axes, right? Fitness, inferred activity, and measured activity.
Sure.
I think inferred activity is taken from this Rubisco flux.
Sure.
And then they fit that to Michaelis-Menten to extract Vmax and Kc.
But they then have two free parameters that they're fitting.
Yeah, they have two free parameters that they're fitting. And that's something that I did. Like I had two free parameters that I was fitting when I did Michaelis-Menten stuff.
Okay. So it's a little bit iffy. They then go on to try to show whether or not what they do works. They don't lie. They show that it kind of works and it kind of doesn't.
Yeah.
In 3F. I think they say it pretty well. They're like, hey, this works, except not 100%. Gives me some faith in what they're doing, actually. They're pretty blunt about how well it works.
Yeah, that there are limitations. And I think one of the limitations that they highlight is that it's hard to separate out how well the protein is expressed from the measured rates.
It's time to complain about this paper. If we can't have fun while doing these
we can have fun.
Apocalypse
Why
papers,
don't you have fun with these papers? This, I think, is a cool paper, and not just for the apocalypse reason. I think this is like, how do you get functional proteins? How do proteins evolve?
Yeah, how do you get proteins? You don't get them by single amino acid changes. I'm surprised that they see anything.
Well, I was not really convinced that they saw anything, right? I felt like when they were describing the data, they were very like, oh, nothing really happened. And then sometime towards the end, they were like, oh, but something happened.
Yeah. So there's two statements in the conclusion. In the conclusion, they say that the fact that they can mutate just a single amino acid and get a change of function, particularly they can make it work better, indicates that the enzyme parameter landscape is rugged with apparent gain of function readily accessible, which seems wrong. I mean, they show what they show, but like a single amino acid mutation is super easy. So if there is a single amino acid mutation that exists and it appears to create higher fitness, greater gain of function, and there doesn't seem to be any measurable downside, it should have happened already, right?
Well, so that's the thing that confused me a little bit, is that they said that there was a gain of function in CO2 affinity, but they didn't show any gain of function in the Vmax or Kc. I feel like you need to gain both functions for it to be an actual gain of function.
In figure 1F, they have a fitness versus density, and they show a couple things where fitness is how much biomass gets created over a certain amount of time.
Yeah.
So I think that is their argument that the single mutation is beneficial.
No, because when they describe that, they say that it's like a very small number of those with a very small increase. Let me see if I can find it.
Well, so they do a deep dive then into two specific amino acid changes, right? And they
do a deep dive in the CO2 affinity measurements, but they don't do a deep dive into this fitness. And the fitness isn't improved for this Vmax, Kcat stuff.
Is that true? Isn't the fact that they have higher fitness mean that the Vmax was improved? Isn't that what that means? The higher fitness does not mean higher CO2 affinity. I could be wrong. It could be that the outliers in fitness are not. Yeah, I am seeing that they never call out these three specific mutation sites as having fitness in the test. I just assumed that the few mutations that had higher fitness as measured by density were the same mutations that had higher CO2 affinity. But I guess I don't actually see that specifically stated. So maybe I'm wrong, that there exists a population of mutations you can do that increase fitness and a different population of mutations you can do that increase CO2, in which case...
Yeah, well, so I think that there's an ambiguity of what they mean by fitness. And that's where I got confused about the findings of this paper.
So this paper, to me, is written really badly. And I want to talk about that a little bit. Okay, so the main thing when I'm trying to teach people how to write papers is that when you go in and put in citations, it is not like sprinkles that you put on a cake, which is how I think most undergraduates view citations. Is something you sprinkle on. Here are some citations. Citations in a scientific paper are like a form of punctuation in which there is a little sentence in your punctuation. This paper starts off with the sentence, plants, algae, and photosynthetic bacteria together fix around 100 gigatons of carbon annually using Rubisco, the most abundant enzyme on Earth. Citation. That citation brings you to a paper called The Biomass Distribution on Earth, which is not a terrible sign, but not a great sign, right? It's not titled Rubisco is the most abundant enzyme on Earth, or plants, algae, and photosynthetic bacteria fixation rates, or anything right like that. The sentence makes two claims: that plants, algae, and photosynthetic bacteria fix 100 gigatons of carbon, and that Rubisco is the most abundant enzyme on Earth. The citation could back up either of those two claims. If you go to the paper and do a Control F for Rubisco, there is no Rubisco mentioned in that paper. If you look around for the claim of fixing 100 gigatons of carbon annually, that's also nowhere in the paper. Now, I'm not saying that the statements of the first sentence are wrong. I'm saying that the citation that they made has nothing to do with the sentence. They just sprinkled it on there. This is the first sentence of the paper. I really try to hammer this home to anyone who I'm like mentoring through writing a paper. There's two or three really important things in writing your paper, and it might be that the most important one of them is your citations. You don't do too many, you don't do too little, you do the right amount of citations, you use them as punctuation sentences to mean things. That was a really long rant. You didn't say anything during. I don't know how we're going to edit it to be less of a long rant.
I'm sorry. I didn't know I was supposed to say something. I agree that citations are super important. And yeah, I am concerned that something could make it into such a large journal and not care about that.
Do you think that this is the worst episode we've done?
Yes.
Yeah. I mean, already like we have an intro that I don't think we can use, and a like 10-minute rant about me about something that I think is super important, but it's both have to be completely deleted. So I don't know what we're going to do. What else do we have to talk about for this paper? I think it would be nice in the universe generally. Like, I think it's like a big 21st century problem that could get solved during our lifetimes. That would be cool to get an equivalent of AlphaFold for function. Mm-hmm. And like, I know that there's tons of people working on this problem. But like, I think it would be worth just sitting here doing many mutation libraries, large mutation libraries, creating training data for function. Because if you could get an AlphaFold for function, I think that would really revolutionize, like we talk about bioengineering, I think it would change fundamentally what the word bioengineering means.
Yeah. I mean, I think that's something that they hint at here. They talk about machine learning efforts. But one thing I was confused about in this paper is that, so they do a functional output here, and that's very cool. But their way of going about mutations is pretty weird. Or like, not weird, but like not interesting. Because it's so unlikely to produce a functional change. There's the single mutation. And so
but what would you have preferred
I would have preferred to take a ton. I mean, maybe it's just technically really difficult. I don't know. I mean, Rubisco is a really large molecule. Maybe E. coli has a lot of trouble expressing the holoenzyme of Rubisco from plants. But there are tons of Rubiscos out there.
To do many different Rubiscos.
Yeah, from evolution, and to look at what nature has already created as a initial source book.
That's a very different kind of training data set, let's say. But yeah, it does feel like this training data set is trivial. That like it's so unlikely that a single mutation can do anything useful. You really expect from just like an evolutionary argument that you're going to need multiple mutations at the same time to move you out of whatever local minima this Rubisco that they put into E. coli. I wonder if single amino acid mutations exist here that work, or because you've put something not native into E. coli.
Yeah.
Into E. coli.
Yeah.
So now you're in a vastly different system than normal.
Yeah.
So actually you're not in any sort of optimized situation, and you can easily mutate into a more optimized situation.
Yeah. And they also talk about protein stability impacting these measurements, and that you're being stable in a totally different environment is another aspect of optimizing proteins. I've found it interesting that in this fitness, in this x-axis of fitness that they show several times, wild type is not in the middle of the peak. that it's more fit than the average or the ones that are catalytically active, which implies that evolution has done a pretty good job.
Sure. I think it just, it implies that most mutations that you can make are detrimental.
Yeah.
There are some mutations that are moving you towards a better situation. It would be nice then, I guess, to take those single amino acid mutations, that population, and then do another series of additional single amino acid and see if there's something that amino acid by amino acid can lead you to a better protein.
Yeah.
You could be like a very strong evolutionary. This would be the walk that it would take if E. coli was using it successfully.
Yeah. Yeah. And then they talk a little bit about the different kinds of Rubisco that are found. This is, I guess, a form 1 Rubisco, and there's form 2 Rubiscos.
Yeah, so form 1 Rubiscos are plant Rubiscos. Form 2 Rubisco are bacterial Rubiscos.
Okay, so I had it backwards, yeah.
I find a sentence in the conclusion confusing. Form 1 and form 2 Rubiscos have different oligomeric states, and form 2 Rubiscos lack the small subunit characteristic of form 1. So, it is surprising that it is possible to traverse the functional space between them with just one amino acid change. What are they talking about traversing the functional space between form 1 and form 2 Rubiscos with an amino acid change?
Yeah, so this is, again, I think that it's unclear what they mean by function in this paper. My interpretation was that form 1 Rubiscos must have substantially improved CO2 affinity compared to form 2 Rubiscos.
I see what they're saying. They're saying that this figure 4C, this cute tiny figure, which is the only appropriately sized figure in the paper, but that's the format of the journal. I'm not going to give them flack for that. They have this cute little figure, and they have a region which they say this is the CO2 affinity for form 1 Rubiscos. This is the CO2 affinity for form 2 Rubiscos. We can make a mutation, and it moves us from one region to the other.
Yeah.
Okay, that's I think that's poorly written. But yeah, I have a lot of red in this paper of whole paragraphs where I don't necessarily disagree with what they're saying, but I really disagree with the way they're saying it.
I mean, I think this paper was essentially what I expected it to be.
This paper to me is a mining effort, and then they've made a little bit of a story with the mining effort.
Like, what are you going to do with this data now?
Well, one thing I would do is I would run all the mutations through AlphaFold and see if I ever see a shape change. Or if you're trying to train an AI, right, you would need access to all the raw data.
I saw this as like a proof of principle paper of like, look, this is a way that we can, in high throughput, measure the activity of Rubisco molecules and try to explore, because this is an effort that's been going on for decades, is trying to increase Rubisco's efficiency. And some of the statements, like one of the things I learned in reading this paper is that this statement that people make a lot, that there's a trade-off between the catalytic rate and the specificity for CO2 is not known, that hasn't been shown, that's speculation. And so to really prove that, you need these kinds of techniques, I think, to explore the function of many Rubiscos and many mutations to Rubiscos. Yeah, that's why I would be excited about seeing a similar technique applied to more native Rubiscos from different species.
And your nervousness on this episode, you're rocking back and forth in your chair, and it sounds like you're on a rocking horse. And I think the microphone is picking it up.
I'm sorry.
So we'll see if it sounds like Lenny is on a rocking horse to the listeners. She's not. She's just on our garbage chairs. Yeah, I thought in my own way to the same point, like it's different. My point is not as deep. But I thought this CO2 versus oxygen affinity trade-off was interesting, that like if you have affinity for CO2, O2 looks a heck of a lot like CO2. Yeah. And you're kind of very close to doing the opposite thing of what you wanted. So you have to be very carefully designed. I thought was an interesting, that you want to be as incredibly attractive to CO2 as you can be while being not at all attractive to O2.
Yeah.
And so you have a minimal way that you can do that. Did you enjoy? Do you know? I know the answer. For something like 1G, where it shows these amino acid things, and then it has this like giant P or K or G, and then sometimes like a W and an L and stuff like this.
Yeah.
Do you know what those are supposed to mean?
It's like how likely that amino acid is to be at that thing.
Exactly.
What are they supposed to, like,
Oh, I actually like this, right? And the reason why I like this is because the color code is fitness.
Okay.
And so you can see going along G, and the y-axis is all possible amino acids.
Yeah. I liked the bottom part of the plot. What do you think that the letter size is giving you?
I've always thought this was the goofiest fucking thing. Ever since I was in graduate school.
It's just for the whimsy?
I don't know. It's like Comic Sans, right? Like the font that people pick for this, there's like one font that people do for this. There's one color scheme, which is this green, yellow, blue, red that everyone does for this. Mm-hmm. And it just looks goofy as hell. And it's on every paper that tries to show any data like this. One person with like deeply bad graphic design choices made a package in like the 1990s, I gotta assume. And then nobody has been like, hey, maybe I'm going to change the font away from, I don't know, it's probably not
it's
actually.
It's not Comic Sans, but
But it's a goofy font. Yeah. It's a goofy color scheme.
It must be a font that like does very well being stretched vertically, right?
It must not, because it looks incredibly goofy when it's stretched vertically. So,
have you tried other fonts?
If I was going to present this kind of data, I would certainly use a different font and a different color scheme. Absolutely. Yeah. But I appreciated the graph nonetheless, even though they do the exact same graph in G and the space use in this, it just kind of seems like just a tremendous amount of the game now is graphic design, unfortunately. Or maybe fortunately, maybe that's a beautiful part of science, is the art part of science, and the graphic design is actually something to be admired and loved. But in this paper, it bothered me.
The amount, like figure 2C, I thought was the most egregious graphic design choice.
Yeah, exactly. It's just like very large things that are very information poor, were very quick to put together, take up the page essentially. And then you have like, figure 4, which is what all figures looked like in the 1980s and 1990s and is like more robust.
Yeah.
Anyways.
Yeah. So, I mean, I guess I'll tell a little story since we're...
Here we go, time. Asya hasn't woken up yet.
The first talk I gave at Princeton when I was a pretty new postdoc, maybe a year and a half in, I gave a talk at the molecular biology colloquium about the project I was starting. Yeah, so I work in Chlamydomonas, and one of the big goals of the lab that I was working in is to engineer the pyrenoid into land plants to enhance photosynthesis. And so I used this as a little bit of motivation for my talk. And then I went through my whole talk, and then it was open for questions at the end. And I'm pretty new to the field. I haven't read up on all of the literature. So I'm going into these questions very naive. And one of the professors in the department asks, so why not just make Rubisco more efficient? And I had never thought of this before. I was like, well, that seems like a good thing to do. And what I said was like, yeah, you should do that. That's what was the first time I was introduced to the concept of trying to make Rubisco more efficient. And what I should have said was, people have been trying to do that for 20 years and made absolutely no progress.
But yeah, you should do that. It's such a better answer. These like shut down people. I'm so bad at this. It's shutting down stupid questions. You're so good at this, where like you have a couple phrases, or I used to work for a professor who, if someone would ask a question, he would just say, that's not a good question. And just go to the next person in like such a quick thing that like there was no recoil from it.
It went off surprisingly well. There was laughter, and the professor was very kind afterwards. I didn't mean for it to come off as aggressive.
I'm terrible at that. I get stuck answering questions that are not reasonable to answer.
Yeah, and so this is one of the reasons why I wanted to read this paper, which I guess we didn't go through. Why did you pick this paper at the beginning of the episode?
Yeah, because it was a terrible episode. Okay, Laina, why did you pick this paper? And I have a meta question.
Okay.
What percentage of papers you pick going forward are going to be algae papers? If I count this as an algae paper, even though you say it's not.
This is not an algae paper.
But let's say...
There's no algae in this paper.
Okay, what would you describe this paper as?
This is a protein engineering paper. This is like what Seth Freyden is going to do in the future.
No, it's got the word biosphere in the very first sentence, right? This is an algae paper. It's got the word algae in it.
Yeah, but it doesn't have any algae in it. The Rubisco isn't from algae. The organisms in the experiments are not algae.
It's got the word algae 6 times in the main paper.
Okay.
How many papers do you think you're going to pick? What percentage of papers are going to have the word algae more than 5 times in the main? Because I'm going to tell you, my picks for this journal club don't have the word algae in the main paper once. Not a single time.
Yeah, but they have like folding or...
Sure. So I've been asking what percentage are going to be algae papers?
Bez, I study algae. A large percentage, 50 plus.
Are we an algae podcast?
We're not an algae podcast. We're a biophysics
by
podcast.
By far the most viewed thing that we've done is got a picture of a diadem on the front of it.
Yeah, so give the people what they want. They want algae. No, I take your feedback that we need to do things that are going to be entertaining to heart, and
just
I will
to make your
more...
job more difficult. Because you are now, like, when we started this podcast, I was in this trap of like I would spend 6-7 days trying to figure out the perfect paper, and then the paper I picked would suck, and then you would pick a banger paper which you like look for 1 second for. I feel like things have flipped, where I'm spending 1 second looking for a paper now, and you spent a long time finding this paper, you spent a long time finding the previous paper, but now I guess we should get to it, which is why did you pick this paper?
I picked this paper because I'm going to go on a job interview for an engineering department.
Wow.
And this is kind of scary for me because I don't have an engineering background. And so I wanted to read a little bit more about engineering efforts in this space and what's known and what's not known and how can we. So I'm trying to optimize algal fitness. And so how can we.
When you apply to places, what department do you say you're currently at Princeton?
I say bioengineering.
You say you're in the bioengineering department.
I feel a lot of loyalty to the Bioengineering Institute.
Sure. But you don't say that you're in the molecular biology department. Because I would say that you are de facto really in the molecular biology department.
I do sit in the molecular biology department, but I don't feel like I'm a part of that department, right?
Yeah.
I go to the retreats of the bioengineering. I feel connected, like just through the admin, really, to bioengineering. And they were very supportive when I was like just a graduate student coming from Brandeis, and that really sticks with me, right?
I see. Yeah.
Not that molecular biology wouldn't be, but it's just they.
I just feel like a very weird thing that we weren't quite warned about when we left our PhDs in physics and didn't go to physics departments. We were told, hey, this is kind of like immigrating to another country. You're really leaving your old country behind. Say goodbye. We understood that. But also there's this thing about immigrating to another country, which is that often the new country really does not accept you as one of their own. Yeah. And I don't think we fully internalized that we are now immigrants for the rest of our lives. And not just an immigrant, but like the country that we moved to, we're not even like sure what country we actually moved to, right? Like it's, I seem to.
Are we in biology? Are we in engineering?
Yeah, it seems like we thought we were moving to like molecular biology, and that's not at all where we were moving, right? And now we're it's like immigrating to Puerto Rico, right? It's like, did I move to America? It's like very unclear.
I like that analogy. It's feeling apropos right now. But yeah, that's why I picked this paper. I guess we could go through some of the questions.
What do you think is intellectually beautiful about this paper?
I still find this problem that Kara is obsessed with intellectually beautiful, of like, how do you get protein function from evolution? Yeah. And so this not obviously, but to me, this was not convincing that a single mutation is giving you is going to lead to the evolution of protein function, but it did seem like and
the fact that it does is deeply suspicious.
Yeah, I think is related to these artifacts, or I don't know if you consider them artifacts, but these things that you're talking about of like
in E. coli,
and doing something slightly different there. But that this could be a platform to test that. Like you could imagine doing this in high enough throughput to make multiple changes, or to see how you can really define the landscape, or going on to get computers to help you figure out what mutations you need to make and how many and how do you get there. I think is a really beautiful problem. Yeah.
So I know it's all buried in the extended data. The version of this paper that I got, the extended data was not accessible. I'm sure that there's other ways I could get it where it would be accessible, but they talk about figure 1A, 1B, and then they have 3 paragraphs of extended data. And then they talk about figure 1C. Those 3 paragraphs with that tremendous amount of extended data, where they have 4 extended data figures which all have their own subfigures. And I don't know what they look like, and I didn't read them. I didn't look at them. And this is, I think, a major problem of what research looks like to the reader now. Is just an absolute travesty and disaster because nobody's reading anymore, and we just shove everything into the supplement. That bit hiding between figure 1B and figure 1C, I really would like to know how hard this is to do. What is the scale of the lab that did this? There's, I'm going to say maybe 20 authors on this paper. Is this a tremendous endeavor? And this is really a huge scale, or it's like a big innovation of this paper of how to make this not a tremendous endeavor. And now people are going to be able to do this 10-fold bigger, 100-fold bigger as they get rolling. I have no idea because all I get is 1A and 1B. And, quite bluntly, I think the most important thing they could have possibly given me in this paper is just a photo of the lab bench that they're doing this on, right? Like that's what I want to understand. And then the data. And I did look it up while we were talking, and the data is all accessible online.
Cool. In
moderately easy to reach ways.
So my impression from reading the paper is that a lot of the work came in not in the pooled measurements, but in the making those measurements physical. So not just taking relative measurements.
Yeah. The purifications, I guess I know how hard the purifications
doing the purifications and doing the like rescaling everything so that you're measuring something in real units. And I give them.
Yeah, but
I'm happy that they did that.
How much effort that is. I'm happy that they did that. Absolutely. Yeah. I know how much effort that is. The main screenings.
Yeah.
That's what I'm unclear on how much effort that is.
Yeah.
And what I'm unclear is that years of one person's life, or is it years of 5 people's lives? That's kind of the range that I imagine it is. And that's what I would like to know. Do you need to have a huge, 5 people is a pretty big team, right? That's like you're spending $1 million a year on payroll for 5 scientists, right?
Yeah.
Is that what's required here? Or can you get away with $100,000, $200,000 of payroll? Yeah, that's my question. This paper also does this thing. This paper has an author correction. What do you think the author correction is?
Some axis was mislabeled.
They mislabeled where 2 of the authors are from.
Okay.
I hate this because you get like a big flyer at the beginning of the thing. This article has been updated, right? You get the same flag if a paper was completely wrong and had to retract part of the data as you get if someone was like, oh, I linked to the wrong citation, or I misdid the author. I would really just update it. Don't tell us. You don't have, if you got the author names wrong, or you put in a micro instead of an M or something like this, you don't need to tell me, right? Just change it. I don't need a giant flag saying that David Savage is actually at Yale, not Harvard. It doesn't, come on.
Yeah, I guess
You're going to disagree just for the sake of disagreeing.
No, I mostly agree. I would like a version history.
A version history would be great. Like the way that BioArchive does it of a version history.
Just you don't need to tell me what you changed. You just need to tell me this, if I accessed the paper 3 years ago and I thought that the axis said one thing and then I'm downloading it now.
But I think it's super toxic that it's so hard to change little things about a paper, like typos in spelling or I forgot a comma. You only need to give me a warning if the science changed, man.
Yeah. But then you have to somebody has to understand the science enough.
If you could have one thing added to this paper, what would it be?
I've talked about it. Other native Rubiscos.
Okay, sure.
Again, I don't know how hard that is to do in E. coli. Is it possible to... Rubisco complex in Chlamydomonas is 550 kilodaltons. Maybe that's not possible to express in E. coli.
As the picker, would you like to talk to Asya for a few minutes on our outro of why you were interested in this?
Yeah, so I guess this gets to your complaint of doom and gloom.
Yeah, I'm going to be Asya. More.
Yeah, so we're just trying to make it so that the planet is inhabitable for you. That's what I'm trying to do. And I think that this...
We're trying to make it so the planet is more inhabitable.
More inhabitable, yeah. And...
Yeah, we talk a lot these days about the math of inhabitability.
Yeah.
Of
changing inhabitability.
What is the excess gigatons of CO2 that we are producing each year? And we did some calculations of if you take every single photon from the sun and use that for CO2 capture in the most efficient possible way, how long would it take to reverse the amount of CO2 that we've dumped into the atmosphere over the past 100 years? And even those numbers are super depressing.
Yeah.
And it just makes it seem that there's 2 endeavors. reduce the amount of CO2 that you're dumping into the atmosphere and start trying to capture CO2 again through like forests and algae blooms. And boy, both just seem totally impossible.
Yeah.
The whole endeavor, it's like the doing the calculations over the past month is the first time that I was like, oh, this is actually an apocalypse scenario, right? That there's nobody, everyone is a snake oil salesman, no one is reversing this clock.
Yeah.
I mean, maybe again,
we missed the talk that at Princeton, we missed Kim Stanley Robinson came to speak about a year ago at Princeton, and we missed the talk because we had a 4-month-old. But some of my lab mates went, and they said that the message behind his talk was that we have the technology to like go to carbon zero and start building CO2 fixation, but we don't have the political will.
Yeah, but I think that's just totally wrong. Like,
you think we just don't even have the technology?
Yeah, I mean, we tried to calculate it, and I talk about this all the time. If someone talked about like, hey, I'm going to make the ocean less saltier, right? Like, I'm going to remove salt from the ocean. I'm going to remove 10% of the salt from the ocean. Everyone would be like, haha, no, you're fucking not, right? Like, that's an absolutely batshit insane thing to say. We need to make the atmosphere less CO2-y by about 10%, and the atmosphere is vastly larger than the ocean. That it's just like a volume thing, that to filter that volume, even if you have 100% efficiency, even if you get every single photon from the sun that you can and go to work for you, just the numbers don't remotely work out.
I mean, then you get to what are we doing with our lives? It's like, I want...
Jokingly, we're trying to make the world more inhabitable.
More inhabitable.
More is Asia's refrain.
Yeah.
Anyways, Asia, this is kind of where our heads were at, both before and after we had you, of thinking about what can you do to extend the habitability of the planet past what we're coming up against. But the numbers are rough. You know, we watch videos of people providing solutions of like, oh, we're going to capture 10 million tons of CO2 a year. We're going to capture 100 million tons of CO2 a year. The huge global engineering things that aren't possible to begin with. And it's like, dude, that's not the number, right? The number is that you need to capture like 100 gigatons of CO2 a year. And man, good luck coming up with anything that captures 100 gigatons of CO2 a year that like doesn't look like
changing the whole planet. Yeah, and so this gets back to these two frameworks that you talked about yesterday. Like improve humanity, like what can we do? What pursuit of knowledge will solve the world's problems, and then also scientific aesthetics, which was our last episode.
Yeah.
So what pursuit of knowledge is beautiful, and so when the pursuit of knowledge, like ideally, we're pursuing knowledge that can advance humanity and solve our problems. But when things look bleak, I take solace, and at least I'm doing something that is beautiful.
Okay. With that beautiful wording, you want to take us out?
Bye.